Okay, well, clearly it's going to be all audible talk. So Jennifer was telling you, actually, I wanted to start with you, Mr. President. So you started off yesterday morning with something that I think is fundamental to what we're talking about here. The point that we know more about the moon than we do about the Earth. And the thing that makes that the Earth. And the thing that makes that true is the ocean. The thing that makes us beautiful and the thing that makes us unknown is the ocean. In fact, that light doesn't penetrate down to the bottom of the ocean. So we really don't know very much about it at all. And so 2 years ago, what we did, the first time I met Jennifer, was we had a workshop to try and understand what was going on in the ocean in terms of the illegal fishing. But what became clear to me at that workshop, and I hope this first slide will come up, I don't know how I managed to break everything, is that the point that Barbara Block was making yesterday at the talk, that we need to get into the media to understand what's going on in the ocean. We spent a lot of time at this conference talking about the surface of the ocean, but we actually have to get down into the water itself. It's a skill. I admit it's a skill. So the ocean, the message that I would like to leave you with, sir, based on you telling us yesterday that you'd like to hear about our ideas, is that the ocean is speaking to us. Not just the animals that live in it, right? But the actual water itself is telling us about the changes in temperature. It's telling us about the changes in salinity. And if I had Google's computing power, and if I had the brain trust that I just saw give that last talk, not me who can't hook up my computer, what I would be doing is spending my time trying to figure out what the ocean is trying to say. Google has done a fantastic job of giving us the visualization. What I'd like to see now is the audioization. I'm going to trademark that word. So
keep talking. We're going to restart things.
Okay.
You're doing good so far.
All right. So the short answer and obvious statement to everybody else who's not Google is every technology that I've heard presented here, please come to Hawaii, come to Palau. Hopefully you've all recognized that none of these technologies are going to solve this problem by itself, right? If we don't hold hands, and one of the things that came up at the Alameda workshop was the idea of stone soup. If we don't hold hands, if we don't all bring an ingredient to the table, we're not ever going to be able to get this solved. So this picture, when it comes up, and it's genius, is the picture showing all of these technologies, from satellites. It actually doesn't have a picture of UAS in it, but it could. It has planes, it has HF radar standing on the shore, and it has platforms in the water. And one of the things that we identified at the Alameda workshop was that we really do a pretty poor job of understanding this water-air interface, right? Right where the ocean action is happening, we actually don't understand very much about what's going on. And so what we've been trying to do is come up with this concept that we call picket fence. And I'll tell you the punchline for the picket fence joke at the end of the talk. But basically, picket fence is an idea of taking all of these technologies and trying to set up a safe zone around a remote island. All right? In our case, we're focusing on KP and Palau. All right? But it could just as easily be your favorite island. Yay! All right. At this point, I know all right, are we going to try and play this now? All right, let's start. All right.
Thank you.
Okay. All right, so here it is, what you were waiting for that whole time. The beautiful picture of the ocean with every kind of technology, and probably two that we haven't talked about, protecting one of our green islands, and trying to both look at our resources, monitor them, and then be scalable and cost effective. And for people I think, that come from Palau, and even people that come from the state of Hawaii, the cost-effective part is really key. Or maybe that's just for those of us that work at universities that are used to the small amounts of money that we get from the National Science Foundation. But I'm not kidding when I say every kind of technology that we've been talking about, I'd like to see it brought in and us to be able to do something. But what happened at that Alameda workshop was we focused very specifically on this air-water boundary and how we could do a better job of detecting what's going on right there. And that brought us to the wave gliders. Now, we've already heard a couple of testimonials about I am or I am not involved with this specific technology. I didn't know the wave glider guys before I started thinking about wave gliders. Full disclosure, they've taken me to lunch 3 times. Jamie has given me a ride here both of these days. Okay, I'm not an advocate just for the wave gliders. WAM-V, wait, I always want to say solar, sail drone, right? Sail drone, you guys have a place in this too. But what appealed to us acousticians about the wave glider is it's such a quiet platform, right? It's a quiet platform. It can move through the water without making too much noise. It can move, which is key. We just heard from NOAA folks that people are coming to fixed assets and doing bad things about them. So being out of the way where people can't come to you every time you know where you are, being able to move is a critical part. And then also being able to collect other environmental data at the same time so that we're finding out more than just what's going on with the noise, right? All of these things are key and made the wave glider our platform of choice. We picked it before we happened to know what was going on for this idea of persistent surveillance. We also assumed, and I'm not an enforcement person, I'm an academic and all that that implies, right? We assumed that bad guys are bad guys, and that if they can find your asset, they're going to steal it, they're going to damage it, right? They're going to try and do something bad with it. And so we had this little experiment end of January off of Kauai High, where we had a whole bunch of people try and find a wave glider that was sending us its position. To be fair, it was painted black. It took us about an hour and a half, and we were driving to where it was. And I have to credit the Coast Guard, because it was one of your Coast Guard guys that actually finally spotted it, being able to do search and rescue. So we envision these guys as being the silent sentinels that sit off of an island and just wait until a boat is coming by that's not supposed to be there. And then they send that information. Hey, there's something that you want to be able to pay attention to. So how come we haven't done this before? How come we don't do acoustics like we do visualization? And I think the answer to this is that everybody thinks that acoustics is hard, which is kind of ironic given that we've just spent almost 2 days talking to each other, right? Take that last presentation, which was wonderful. If they're not telling you what you're seeing, and you're just looking at that, right? You're not getting a whole bunch of information. Assume that one of you was so rude as to potentially leave your cell phone on, right? When I'm giving this talk, and suddenly it goes off. All right, everybody knows where the cell phone went off, right? It went off over there on that side of the room. It's my cell phone with the plans, total plans. But the reason that you know that is because the sound comes into one of your ears at a slightly different time than it comes into the other one of your ears, and your brain automatically processes that, and you know where the sound was coming from, right? So these are algorithms that people should be able to translate, just like we translate edge detection or visualization. We should be able to translate what our brain is doing to be able to take that into a computer and figure it out. How many of you guys are parents? Have you ever had the experience that you're in a game or a park and your kid cries out,
Mm-hmm.
and you know
Yeah.
that was your kid, right? That's pattern recognition. You're able to recognize their cry, their tone. If we can do that, we can teach a computer to do that. And I think that's what we should be doing with the oceans. So I'm going to help you visualize sound right now before, actually, I was supposed to play, will I be able to play the, let's see. I'm usually not technology challenged, although at the airport when I was practicing this, suddenly it jumped into Green Day on iTunes radio. Everybody, wow, what's that? Let's see. Oh, sorry. No. All right. What do you hear?
Nothing, Chris.
Rain.
Okay,
Right?
no.
I didn't have to train you. But if you keep listening, we'll just get about halfway through this. See that consistent, it's actually an approaching boat. Very good. So the one thing that you guys can't do, and hopefully if I scroll through this a little bit, is you can't bandpass filter, right?
There are headphones that do.
Yeah, that's true. It's very quiet. Oh. Here? Just a consistent hum. That's our hope. Okay, so I don't need one. I'm not technology challenged. All right, so stop with the noise. So what you can't do is bandpass filter, but that's a pretty easy thing for us to be able to do in a computer world. So this is a spectrogram. Low frequency sound, high frequency sound, that's something else you just automatically know, right? And this is time. And this is just a generic day on a wave glider when there's not very much going on. This is an electrical noise that's coming across the top. And for the most part, there's not much going on, except down here, these little birds that you can sort of see. They're flying at low frequency. Anybody have any idea? Yes, marine mammals, Hawaii. Whales, right? That's whale song down there that you can hear. All of a sudden, if we add rain on top of that, right? Same day, colors change simply because yellow means that there's more energy pretty much across every frequency in the spectrum. Then it becomes difficult for me to hear what's going on with the whale song. Ironically, now I can see the spinner dolphins. Finally, if I want to be able to track man-made, right? Signals that are consistent, non-changing. So there are all kinds of things that we can do in the oceans with acoustics that are going to help us be able to understand the message that the ocean is trying to tell us. At this Alameda workshop in 2012, we became all these people that you see on the list. Jennifer has been great, and Lou have really been trying to help us. One of the things that happened that I think was really important in terms of the stone soup concept was the Coast Guard. We really sat down finally, and we rolled up our sleeves and we said, what's your ingredient? What can you bring to the table? And Bob Hendrickson, who's there representing the Coast Guard, who's a captain now, who's in Bahrain, he basically said, look, what happens with the Coast Guard is we have our budget 5 years out. If you guys want us to be able to make a contribution, if you guys want us to buy a piece of instrumentation, it's never going to happen. On the other hand, what I have is a ship that costs U.S. federal taxpayers a fair amount of money, and I can take my ship and I can run it through your test area so that you can see how your system is performing. And so that was the conversation that actually got us started with thinking about the fact that it doesn't always have to be about money. In terms of trying to make these things come together, what we need to be able to do is bring people with different talents, different technologies, different experiences, and literally jump into a problem together to be able to solve it. In terms of the acoustics, one of the stories that I wanted to tell you are Stevens Institute of Technology. So being able to identify a ship and hear a specific ship. I know if you're a lawyer in the room, you're instantly thinking about ITAR issues that are related to that. But at Stevens Institute of Technology, which is in Hoboken, so right across the river from Manhattan, they've been listening to the Staten Island ferry go around the island for a long time. And one day they just noticed, as they were doing the regular recording of the ship going through the channel, that it sounded weird. And they called them up and they said, hey, you guys, is there something wrong with one of your engines? And lo and behold, they had an engine problem that they didn't even know about, but the acousticians listening to them were able to tell them so that they could go fix their ship, right? Acoustics is a really powerful tool that we stay away from because frankly, it involves a lot of math. So, what we came up with in Alameda, with our shirt sleeves rolled up and people actually bringing their different things to the table, was an idea to put a towed system with an passive acoustic receiver behind a wave glider and try taking it off fly high and listening for different ships and listening for the environment. And basically, here's where we've gotten. In 2 years, the engineering integration has been done, and I got to credit the liquid robotics guys who've done almost all of the heavy lifting on what's gone on here. We've had multiple deployments to try and improve what's going on. We're starting to do the acoustic algorithm development, and of course there's always vessels of opportunity. We haven't asked the Coast Guard to come over and run through, frankly because at this point we don't think that we're quite ready yet in terms of the algorithmic development. But from 2 years ago to what you see right there in January during a deployment, we're starting to get really close, I think, to being able to look at this near surface layer of the ocean. Phase 2 is a demonstration project. Not only do we have the opportunities and the ideas, but we have KD come and say, I have the need, and I'd really like you guys to be able to take the system out and deploy it for multiple months. And we're going to try and do that in July of this year. All right? So something that's really happening. To be able to demonstrate both the presence and behavioral characteristics and the persistent monitoring of the environment. So one of my forehead slap moments, and I have a lot of them, that's why I look like this. I sent some guys over to Somalia to try and do acoustics of a captured Somali skiff. I didn't know, I bet all you enforcement guys knew, the captured Somali skiffs and the Somali pirate vessels and the fishing vessels, same vessels, right? Same engines. The difference is, one of them doesn't want to scare the fish, so he goes, right? Another one goes, that's the whole difference. It's the behavior of the acoustics that's going to tell us how these folks are doing stuff, whether they're good guys or bad guys, right? The persistent monitoring of the environment, right now, we're really at the position where we just don't know what it is that we don't know, right? So how does rain affect the signal? How do we have differences when the biology's coming up to the surface and when the biology's going back down? How does a windy day affect our ability to be able to hear stuff versus not hear stuff? And just generally, what's going on in the ocean? Those are the questions that we're trying to get the answers to. So hopefully in July, we're looking at deploying multiple units. We'll see. And we are still talking to the Coast Guard about trying to get some of their ships involved in this operation. So, okay, take-home message. This is my joke about Picket Fence. When liquid robotics and we were first talking about this beautiful diagram came out, and I said, oh, it looks like a string of pearls. Let's call it the string of pearls, right? And I made the mistake of saying that to a man, and he said, picket fence. No. So, it was a boy-girl problem. But the idea is basically the same. Take something that's precious and surround it by some sort of protective layer that's going to at least not get every bad fisherman, not get every bad guy who's doing all of these different things. Okay, basic research is not bad. But be able to listen and hear people that are coming in right into your area so that you can react quickly and do something about it at that time. And going back to the request for if I was clean for a day and I really wanted to be able to persistently solve these problems, what I do is I look at the fact that we have this confluence of things, that confluences I think are more important than low-hanging fruit. We have the capability to stay out for a long time with the liquid robotics wave glider and other platforms, okay? We have acoustics catalog that we've been collecting that aren't classified anymore, that tell us about sounds in the sea. And we have the ability to do huge amounts of computing. I was blown away. I mean, 300 years in 2 days? Give me a break. Can I have a job? No. So when these confluences come, that's when I think it's time for us to step up to the plate and be able to do this stuff. Sorry that it didn't get off to a good start. That's my contact information. I did not put this together by myself. Bob Hendrickson, I think a lot of you know Midori Akamine, and Phil Gilliberry, helped me with this presentation, except for the part where I had to hook it up. Thank you very much. So right now we're looking at ranges of, the best that I've heard is about 10 miles to be able to listen for these kinds of detections with this stuff. And if you really want to get into the acoustics of it, I can tell you that they're doing this really neat stuff with broadband acoustics, where you sort of use the bandwidth to be able to tell you how far away something is, so the frequency you're listening to. I could geek out about that for all day, so probably don't want me to do it for me.
Okay, I have a question. So this is great. It's great, but it's kind of like academic research about nuclear fusion, you know, or fission. There's been some government research that precedes this, but it's not really available. So I mean, certainly if you were to go to SPAW or look through the archives, I'm sure you could find something useful, you know. And people that, like the Raytheon Store Detection System deploys sonar buoys around a ship, and you can tell if people are pushing it, SEALs have guys from the other team. There's a lot of military assets that one would think from reading open source material do things like this. Is there any possibility of building a bridge between your work and government work, and just asking, what could you possibly tell me that's innocent and harmless? I mean, have you tried like buddying up with Navy Office of Naval Research and Development or something like that?
Sure, of course, and almost all of the acousticians are actively doing both.
By them? Yeah.
That's right. So they're doing both kinds of research.
Okay.
And it's kind of a fine line that they walk. But what's new about what we're doing here, a lot of the existing research was not done in this upper part of the ocean. Okay, that's part of the ocean where we typically try and get down below, because you do have so much noise. And now, you know, basically thanks to 9/11, we're starting to finally focus on these shallow areas.
Right.
And so there is a lot of communication that doesn't take advantage of all that old deep stuff. But in the shallow areas, we're working together.
Okay, that's interesting, because I was like, you know, like in the past it was like a deep military submarine, you know, Cold War kind of research topic. And here in California, you know, it would seem, it's well to understand, that certain drug smugglers are using submarine technology to bring things from Mexico to California.
Yep.
And so the more police-type people, as opposed to Coast Guard, the less submarine people and more maritime enforcement people, are starting to ask questions about undersea sounds that shouldn't be there and stuff like that. Right. It seems like there might be some loosening of past research results that could be useful to save the oceans.
Yeah, and it's interesting that you bring that up. So up in the Arctic, the submarines that have been going under the ice canopy for a long time, they have been releasing sort of the biological sounds that they've been recording up in the Arctic, so that we can add those to our catalog. So really old data, it's no problem releasing it, especially if it's related to mammals or submarines that no longer exist.
Great.
Yeah, real quick to your question, Mike. The actual system you're talking about is actually commercially available. In fact, in May, if you want to buy one, I have no problem selling it. But in actuality, what it was a lot of the cold or the old technology brought into the commercial world to be able to detect. I only had 90 seconds yesterday, but to be able to detect and point to it.
Right.
And the reason why we went to acoustics was, one, if AIS is not transmitting. The same thing is with the semi-submersibles. You can still hear it, but it's difficult to see, or even the loud submersibles that the drug runners use. So when we did that, working really close with Margo and her team, we were able to actually get it out there and operational and sort of cut through that because of the experience that they had.
It just seems like there's sometimes military things for non-military purpose, for public good. You can weasel out some results that could be helpful to people.
Yeah, time to go to the project.
We've all paid for that in our taxes, right? It's not like we have to, we did it again, you know, it's borrowing.